Hi everyone. So today we're going to discuss the concept of using graphical methods and solving the problem of maximizing or minimizing a linear algebraic function subject to certain constraints. To understand what this is, I recommend you to first go through this short 7-minute video, Mathematical Programming 1, Graphical Methods under Works After College. And once you go through this, you will understand what we are actually trying to solve and how to mathematically solve it. In this lecture, we will be talking about how to solve it via code, and I will be running through the options that are, the code that is here, and I'll be implementing whatever is taught in this particular video itself. So to begin with, we're going to write a code in Python. We need certain libraries. We need matplotlib to actually plot the graph. We're going to use NumPy because we're going to deal with matrices as the variables that we have here, the different equations that we have here. The way you solve it in a computer is you use variables and you solve it using different libraries. And NumPy is the most popular Python library available for any kind of matrix related or linear algebraic related functionalities. And without further ado, going ahead. So we are trying to solve this particular question. I will paste it here also. So what we're trying to do is we're trying to maximize a function 20x plus 15y subject to certain constraints. So given this constraint and this constraint, two equations, 2x plus y less than equal to 18, 2x plus 3y less than equal to 42, and x and y must be positive. Subject to these three constraints, we're trying to get the maximum value of this. So to begin with, we want to understand what these two equations actually mean. And if we were to plot it manually, what we would do, we would substitute x equal to 0, find y value, and we would substitute y equal to 0, find x value, and plot it. And that's kind of exactly what we will do, but we will do it in a slightly different way. So we will get those endpoints and all later.
Can you just zoom a bit into the document?
In this,
No, the Word document.
I will be copy
Okay.
pasting this, so you don't have
Yeah,
to worry.
sure.
I'll be pasting those items here, so it's not
Yeah.
going to be a problem. So what we're going to do, we're going to try plotting this graph first. So going through each of these functions, line space is basically to plot a given graph. And we have some constraints. Under those constraints, we're trying to plot 2x plus y less than 18, 2x plus 3y less than 42, and xy greater than 0. So how are you plotting it? Now you can notice 2x plus y less equal to 18. We're plotting the equality graph instead of the less than equal to graph. So when we get the graph, we can see that whatever is under the curve is what we will be considering. If it is greater than, we will be considering what is above the curve. Now, the way I'm plotting it is I need to pass in my values, and I will have certain plotting things. I will talk about this. Just give me a second. So what we're doing here, we are creating a plot. In the plot, I'm passing my x value, I'm passing my y value, and I'm passing a label just to indicate what line that is. Similarly, I'm passing another x value, another y value, and a label. So x value, you might be wondering what this exactly is. So it's nothing but like an array between 0 to 50, starting from 0 all the way till 50. And you are spread with 50 variables. You get 50 values in between that. So you can see it starts all the way from 0, 1, 2, 3, and all the way till 50. Only difference is you don't see it as 0, 1, 2, 3, 4, 5. Like you can actually have, 0, 1, 2, 3, 4, 5 all the way till 50, where till 100, sorry. So 0 to 100. You will have 100 values between 0 to 50 here. You can have it as 0, 0.5, 1, 1.5, 2, 2.5. The reason it's not a straightforward thing is because they're trying to normally distribute this. If you're not aware of what normal distribution is, you don't have to worry too much about it. It's just about trying to even it out using a concept called statistical normal distribution. So this is what X contains. And if you, the values that you see here, 0, 2, 4, 6 in the X column, that is what these values are corresponding to for us. Now for each of those values, I'm passing it as X. And for my Y, I'm passing the modified value for Y, which is basically 18 minus 2 into X. This, so you send 2X to the other side, and then you do Y equal to 18 minus 2 into X. And similarly, for 2x equal plus 3y 42, you send 2x to the other side, so it becomes 42 minus 2x. And the 3 goes to the denominator, so 42 minus 2x whole divided by 3. And I will pass that as well, and I will have a label for that as well. You don't have to worry too much about what all this is. This is just for displaying it and to. So if you're interested to learn more about what plotting is and all, you can go look up what this matplotlib.pyplot is, or matplotlib in general as a library, and you can figure out how to plot these different functions that you have. So I'm going to put that. The limit is nothing. We're just trying to restrict how much of it you want to plot the graph. If the values are more than like 100, 200, you don't want to really plot them because we are not interested in all that. We are looking only at a certain limit. So it's just like saying, although it's actually there mathematically, you don't have to show it. Legend is basically just going to display. I will show it you in just a short while. So let me run this. Legend is basically the one that you see at the top. The small box is to display. And when you say plot.show, it'll actually calculate this, and both of these plots will be plotted onto the graph. Now here you can notice the orange line is basically a 2x plus 3y equals to 42, and the blue line is a 2x plus y equals to 18. And here we have a different x values, 0 all the way till 30. So this actually runs till 50, but it's getting off cut at 30 and 30 at both ends because we have applied our limits here. Now the question is, we need to figure out, given these constraints, we need to plot this particular z value. Also, x and y greater than 0, and we're not considering into the negatives. So you can also see we are not looking at the negative coordinates already here. There are ways to add the negative coordinates as well. It's just that you need to change the way you plot, and there are some other functionalities. You can go back and look at matplotlib library if you're interested. So under this, we are having less than equal to as our constraints. So that basically means whatever is in this small area here, this is where we want to basically figure out what our maximum value for the given function is. Now, let me remove this. So now that we have our graph, the next thing we want to figure out, if you would have looked at the video, is basically the intersection points, the end points. So how would you basically calculate the maximum of a given function? You know that this particular orange line here, and then this blue line here, and these two black lines are corresponding to our given considering area under the given constraints. And we look at the extreme points, that is this particular point here, this intersection point here, this particular point here, and the origin point. And for all the four values, we are going to plot it for this particular z value and see where it maximizes, and that will be our answer. So how do we do it programmatically? For that, what we need to first figure out, we need to figure out the endpoints. We need to figure out this particular point, the intersection point, and origin. To begin that, what we will first do is we will define a function called endpoints. So what is this endpoints? Given a line cx, cy, cb, that is basically and b, which is defined as as it's already mentioned here, you would have cx plus cy equals to b. this is how the line is going to be represented. Given the line is represented in that format, uh, what we're going to do is we're going to find out the endpoint. So for example, given the line 2x plus y equals to 18, 2x plus y equals 18. So what this means that x equals to, cx is equal to 2, cy equals 1, and b equals to 18. Now, if you notice this line, 2x plus y equal to 18, you can see that it has two endpoints. One is when you substitute y equal to 0, x becomes 9. So that is 0, comma 9. 9, comma 0. So this point on the x-axis for the blue line is 9, comma 0. And when you substitute x equal to 0, this is 18, 0, comma 18. So given this particular thing, we need to, if I give cx is 2, cy is 1, and b is 18, I need this method to return me two values. One is basically uh, 0, comma, I mean, 8, comma 0, 9, comma 0. And the other point it should return me is 0, comma 18. Similarly, for the other line also, we need to do the same thing. So how are we going to do that? First, we're creating an empty list, which is going to eventually contain both of these values. And then we're going to have coordinates of the first endpoint. So we have two endpoints. This is one endpoint, and this is the other endpoint. And both of this is going to be put in one list. So where both of this is going to be put is in P, and where the first endpoint is going to be put in P1, and the second endpoint is going to be put in P2. So initially we are just creating an empty list, and we're not putting anything into it. And then we want to put something into it. So what we're doing here, we're appending 0 into this. So actually what they're doing is, they're doing it this way, with P1 equals this, and P2 will be equal to this. So what are they doing first? They're first appending 0, because we need the endpoint on the y-axis. And on the y-axis, x coordinate is always 0. So first we will append 0 here. And then the simplest way to just find out the x coordinate is to do 18 divided by cy here. Because the way we calculate it is we consider the y coordinate to be 0. So we really don't, x coordinate to be 0. So we don't care about what is the coefficient of x. It's just going to be 18 divided by the coefficient of y. So b divided by cy will get us this particular 18 value. So that's going to be 18 divided by 1 in this case. Similarly, for P2, what we're going to do, first we're going to do b divided by cx here, because we're going to do 18 divided by 2 to get the y coordinate. And then we're going, the x coordinate. And then we're going to append a 0, because we need the 0 on the x-axis here to get this particular point. Once I get those two, I'm going to put that into my return statement, appending it onto P, and I'm going to return my P, which is basically giving me my endpoints. So if you want to quickly try this out, you can, by the way, this is called Jupyter Notebook, where you can enter your code and you can test it out right then and there to see what actually happens. So our example was basically giving cx is 2, cy was 1, and 18. You can notice we are getting 0, 18, 18.0. It's just a float number. Don't get confused. And 9, 0. These are the two values that we're getting. Similarly, if we look at the other value, 2, 3, and 42. We're looking at 2, 3, and 42. We're getting 14, 0, 0, 14, and 21, 0. Sorry about that. So these are our 4 endpoints. Now, where do these 4 endpoints represent? This is 0, 18. This is 0, this is 0, 18, sorry. This is 9, 0. Then we have 14, 0, 14, and we have 21, 0. So we have 1, 2, 3, and 4 points. So now the objective is what? We need to get the minimum of these 4 points. So if I ask now, depending on the constraint, our constraint says less than equal to. Because it's less than equal to, we want to consider the inner points here. This one and this one. So we should consider 0, 14 and not 0, 18 because it's less than equal to. And here we need to consider 0, 9, 0 and not 21, 0 because this is the inner point and we need the intersection point as well. So now the next thing we're going to try is to get these inner points along with the intersection point. So how are we going to get the intersection point? I'm not going to go deep into this, but what I'd suggest you to do is go through this method called Crammers Rule. So this is called the Crammers Rule, where if you're given two equations like a1x plus b1y equal to c and a2x plus b2y equal to c2, the way you find out the value for x is basically you use this formula where you have your coordinates, your constant c1, c2, and your y coefficients b1, b2, and you get the determinant of them divided by the matrix determinant a1, a2, b1, b2. So once you do that, you get your value, you get your coefficient for x. Now, similarly, for y, if you want to do, instead of b1, b2, you actually go, the c1, c2 goes to the right side and the a1, a2 comes to the left side. And the way this is done, the intuition, higher intuition is you want, given y, you want to, nullify the this particular coordinate, a coordinate. So that's why you're adding it here. And because this is the x coordinate, it's on the left side. And b1, b2 is to nullify the y coordinate. And b1, b2 is on the right side because it's corresponding to the y. And the constants go on the left here and the right here. And once you solve it, for deeper understanding, go through this, Google it or look at some videos online or anything else. I'm not going to cover that here. But using the Crammers rule, basically you can find out the coordinates of x and y. Now, all you need to know is this formula will yield you the intersection point between these two lines. Now, because I know this, what I'm going to do, I'm going to go ahead and implement a function called line intersection, which is going to use the Crammers rule. And given two lines, I'm going to find the intersection point of the two lines. So here, what am I doing? I'm giving it 6 coordinates, a1, b1, c1, a2, b2, c2. So here a1, b1 is nothing but this a1, b1, c1, a2, b2, and c2. So given all these 3 coordinates, what am I doing? I am going to apply this particular formula that you see, c1, b2 minus b1, c2 divided by a1, b2 minus b1, a2 for x. And for y, this particular formula. I'm simply going to go ahead and, this is dx. I'm going to substitute it there. For dy, I'm going to substitute it there. Okay. And this is basically the numerator part. C1 B2 minus C2 B1 is this numerator part. And you can notice A1 B2 minus B1 A2 is common for both, which is what is my D here. So I'm going to have dx divided by d for my x coordinate and dy divided by d for my y coordinate. And whatever I get, I'm going to return. And now how am I going to get the value? So basically if I do intersection of this, I want to get it for this particular line and this particular line. So these two lines, I want to get this particular intersection point. And the way I'm going to do it, I'm going to send in my coordinates 2, 1, 18, 2, 3, 42. When I say this, it gives me 3, 12, which is an intersection point. So now we have multiple points. We have this particular endpoint, we have this endpoint, we have this endpoint, we have this endpoint, we have this intersection point, and we have our origin itself. Now we need to apply our constraints. We don't want the outer parts, we want only what is inside. So out of all the given points, we want to find what are our feasible points now. That is where our next method comes in. So this method, I am not really sure. I think there is some issue here. But I will go ahead and explain. So these are the notes given by the course coordinator. We need to double check this particular code once, but anyway, I'm going to run through them quickly. So this feasible thing, what it does, so what are the different points we have? We have 3 comma 12, and then we have 18 comma 0, sorry, 0 comma 18, and then we have 9 comma 0, and we have 0 comma 14, and finally we have 21 comma 0. So by intuition, looking at the graph, you can just say that, I need to pick this because it's the minimum point. I need to pick this because it's a minimum point. I need my intersection, and I need my coordinate itself, 0 comma 0. So now, what should my method basically return? The feasible endpoint method, if I give all these points into it, I need to basically get this particular point, this particular point, and this particular point. This is what it should return me because these will be my extreme points. And I will be applying this on this particular z function to find out where the maximum is. Now, how do I find out what is feasible here? Is this particular method. So what I'm doing here, I'm running through x. X is nothing but basically this is x. Wait. X is nothing but a list of all this. So a list of all these values. I'm not considering 0, 0 here because we're trying to maximize it. So, I mean, in reality, you should be considering it. If you're trying to minimize it, it makes more sense. Or if your coordinates are into the negative aspect of the quadrant, the coordinate axis, then 0, 0 makes more sense. For intuition purpose, I'm leaving it out here. So out of all these pieces, we need to basically give this as my capital X, I'm sorry, which will be my input here. And my output will basically should be a list of these values. So yeah, you can notice that's what happens here. Okay, I think the way they're implementing here is a little different. They're actually not considering the intersection point. They are already taking the intersection point later. So this will not be coming here. So they're only looking at this endpoint and this endpoint. What is the most appropriate? And I think they're just going to add in all the list of intersection points that are required. So the way they're doing it is they're going to run through each of these x's. So in this case, for the first trial, we'll have I equals to 0 comma 14, and for the second trial we'll have I equals to 0 comma 18, sorry, my bad. Second trial we'll have 0 comma 14, and then we'll have 0 comma 9 comma 0, and finally we will have 21 comma 0. So here what are we doing? Basically we're looking if this value is 0, basically if the x coordinate is 0. If the x coordinate is 0 and this particular coordinate is less than y. Y we have set it to an arbitrarily high number. It doesn't have to be this. It's just that it's like saying, it's a very high number. We need numbers less than that. Because it's going to be less than. So because this happens, we are having y of this. What we're going to do, we're going to put that particular value into p. P will become 0, 18 in this case. And again, next time when it runs, we will come to 0, 14. Now again, so here I think what is actually missing is, just confirm this with your course coordinator once. But I think there should be a y equals to I of 1 here. Basically, you are trying to find the minimum of these two, right? So here initially I'll have 18, and then the next time, so next time if 14 is there, because 14 is less than 18, we will replace p with this point instead of this point. So at the end and when it comes to the third iteration, I of 0 is not 0. So this thing will, these two will not even go into this particular loop. So this loop is to find out this particular point, the first point, this for loop. And the second for loop is basically the same thing, but instead of doing I of 0, we're doing I of 1, basically saying, these two will not even be considered here. 3 and 4 considered. This is the value that is chosen. These two are not considered at all into this particular first for loop. In the second for loop, what happens? These two are not considered this time. The first two will not be considered because I of 1 is not 0. That is a requiring condition here. And here we consider this and this, but because minimum is there, this is chosen. So if you look at how we're going to run through this iteration, we come here, I of 1 is not 0, so we skip this. I of 1 is not 0, so we skip this. I of 1 is 0, and I of 0 is less than x1. x1 is also an arbitrarily high number. This can also be 999. There's no reason for it to be 100 or whatever. It can be any value here. Doesn't matter. It should just be a big number. So let me put that also for just for readability. Now, if your particular value, this particular value is less than the current x1, this value, what we're going to do, we're going to replace this x1 with this particular value, and we're going to put that into our P1 position. P1 is nothing but this particular point. This is called P, or for readability, what I can also do is I can call this as P1 and I can call this as P2. Okay. So yeah, what we're going to do, we're going to put that particular point into P2 if it is less than that value. So next time, second, we put 9, 0. Next iteration, all the 21, 0 satisfies the first condition. The second condition, I of 0 less than x1. Now x1 is 9 and I of 0 is 21. 21 is not less than 9, so it will skip this loop. At the end, P1, P2 will consider what it will have, 0, 14 as P1 and 9, 0 as P2. To quickly run this, what we're going to do is we're going to give it all these points. So I'm writing it in this form here, but understand that we are sending them as lists. So I'm putting square brackets here and not the other brackets. 0, 18. My bad. 0, 14. 9, 0. 21, 0. So you can notice that we're getting 14 and 0. I think this is right because if the statement was not present and we had this way, Okay, it still works. Oh, one sec, sorry. Yeah, it doesn't work. So this has to be there. This is missing in the code. Just check in once. Y equal to I of 1 must be there. So what this gives, this method gives us this particular endpoint and this particular endpoint, and we have a junction point too. So we have something called final points n. So what we will call it, we will call it as final points. Final points is nothing but it's going to be feasible thing of this. So how are we going to do this? Instead of like writing it manually, what we are rather going to do, we're going to give it some parameters. We're going to give it variable names and we're going to go for it. Okay, now we have y and y1. So what we're going to do, we're going to we need to find endpoints first. And endpoints of this, I'm going to call it line 1. Endpoints of this, I'm going to call it line 2. An intersection, I'm going to call it intersection. Okay, and here, so I'm going to execute this again and this again. And intersection, instead of passing, okay, and once I have my intersection points, my feasible points are basically going to be line 1 comma line 2. Give me 1 second. Yeah. Madhav, cut this off later, no? The small part.
Yeah.
So what we're going to do is we're going to have, I'll do one thing. I'll change that from there to here. These are the steps we're going to do. We have our first equation. We're going to get our endpoints for the first equation. And then we're going to get our endpoints for the second equation. And then we're going to find the intersection point for both those equations. And we're going to get the feasible points for those two equations. And finally, we're also going to add the intersection point into the feasible value. So these are the different steps we're going to do. This is what we spoke about earlier. We get the endpoints, that is basically this point, this point, this point, and this point. Then we get the intersection point, which is this point. Then we get the feasible endpoints, which is the lowest of them because the constraints are less than. So it is this point and this point. And then we also append this particular intersection into that. That's what these few lines mean. And once I execute this, final points will basically have 14, 9, and 3, 12 will be our intersection points. So these are our constraining points that we finally get here. So if you look at this video, the table that you get here in the end, these coordinates 0, 0, 8, 0, 6, 6, 3, 12, and 0, 14, these will be whatever final points we will be getting here. And now it's just about substituting into the formula for Z and finding out where it is maximum. So now our last method is basically going to be our objective function. We're going to have something called the objective function, which is nothing but it's going to give us given z, it's going to calculate given x and y, which if you give these two values, it's going to calculate z and it is going to return z for us. So to give you a brief, if I say objective function of 0, 14, sorry, is going to give me 210. Same if I give objective function of 9, 0, going to be 180. And finally, if I give it 3, 12, it's going to be 240. So you can see that 240 is the point of maximum out of the three, and our answer should be 3, 12. But how do you do this programmatically? It's very simple. We're just going to write a function. So what we're going to do first, we're going to write a function which is basically, we're going to create a list. So what this list is, we will call these z values, indicating 210, 180 and 240. Whatever values for z is there, those values are going to come into the z values list. And what am I going to do? I'm going to run through this final points, the entire range of final points, and I'm going to apply this particular objective function, and I'm going to just pass in these two values, the final points of I, 0 and I, 1. Don't be confused. All I'm doing is I'm running through this particular list and I'm passing the 0 and 14 into this objective function, and then I'm passing 9 and 0 into this objective function, and 3 and 12 into the objective function. And I'm just adding those values into the z values.append. So if you notice what the values of z values are, you will see that they're nothing but 210, 180 and 240, which we calculated manually before. I have done that using code. You can do that for how many ever values you have. And now once I have this, I need to figure out which is the maximum values out of these three, and I need to get that particular, z value accordingly. So 240 is the maximum. How are you going to do that? We're going to have another small function, which is basically this. So I'm going to call this maximize. I'm just changing the name because I feel it's more relevant. So here maximize, what am I going to do? I'm going to send in certain parameters here. We'll come to that in just a minute. So we have something called m, which is used for holding the maximum value. So m is going to be nothing but our max value. I'm going to change it a little for our readability sake. And this will be the coordinates. Max value is here and here. And coordinates. And here m and n we have. N is basically our final points. So I'm going to keep the same conventions. Final points 5. And m is going to be use for holding coordinates range of m. What did they send to m? That is m and c.
Yeah.
And here, instead of m, we have our convention of using z values. So I'm just going to change this to z values because we want the largest of the z values. So what are we doing here? Nothing too complex. We're getting the maximum value. So we're considering the first value to be maximum, and we don't have any coordinates now. So for every value in this, in the particular z value, we're going to iterate through each of these, and we have maximum value, which is currently 210. If it is less than or equal to the z value of I, basically 210. First, we're comparing 210 with 210. If it is less than or equal to, like if this value, the value from z value is greater, then I'm basically replacing max value with this particular value, and I'm setting the coordinates to this particular corresponding coordinates. So 210 was given from 0, comma 14. So max value will become 210 and coordinates will become 0, comma 14, which is coming from our final points of I. And again, I'm going to run. Now I have 180. Max value, is it less than or equal to 180? No, max value is 210, which is greater than 180. So I will skip 180. And finally, I have 240. Max value 210 is less than 240. Because it is less than 240, what I'll do, I will change the max value to 240. And my coordinates will become whatever are corresponding to 240, which is nothing but 3, comma 12. So coordinates will become 3, comma 12. Oh, okay. Yeah. And what am I going to do? I'm going to send in my z values that we calculated earlier from here, along with my final points, which we calculated from here. And it should give me the particular intersection point and the max value 240 and 3, comma 12. So this is the graphical method. So if you notice here, they have multiple points, but the greatest value is at 3, comma 12. This is a different problem, but I'm just giving you insight if you go through this video. At 3, comma 12 is the greatest, and because we are also trying to maximize our z function, our maximum of z is 240 at 3, comma 12, given these two linear equation constraints. You can go ahead and add how many ever linear equations you want. It's going to be a very similar process. It's just going to have multiple lines here. You're going to have other endpoints, feasibility endpoints. You might have to modify the feasibility endpoints, or you will have to add your intersection points into this place while finding the intersection between different points. And more or less everything else is going to be remaining the same. If it changes to minimizing z, then a few things will change. Instead of max value, you'll have min value. The function will change to minimum. The greater than signs will change to less than signs. Um, and also your constraints will generally change, because when you have minimizing, it won't be less than equal to constraints. It will usually be greater than equal to, but it depends on the problem to problem. And when those changes, you need to come to the feasibility function, that is your feasible endpoints, and you need to change your approach according to this. This is the code to solve a given equation and maximizing and minimizing it constrained to two linear equations using Python. Please go through this video for better understanding as well. Thank you.